Welcome to all of you. Now we discuss Group B Unit-3 2022 Biomathematics Semester 5 CBCS Mathematics Honours, University of Calcutta. Question paper 2022 Unit 3. Question 8a. Draw the Cobweb diagrams of the one-dimensional difference equation xn plus 1 equal to rxn for different values of the parameter r. Question B. When is a steady state of the one-dimensional system xn plus 1 equal to fxn said to be asymptotically stable? Discuss the stability of the steady states of the following one-dimensional model xn plus 1 equal to lambda kxn whole divided by k plus lambda minus 1 xn, where lambda and k are positive parameters. Cobweb diagram without solving the nonlinear first order difference equation xn plus 1 equal to fxn. This fxn is a nonlinear function. We can determine the behavior of the solution of the difference equation 1 by Cobweb diagram. It is a graphical as well as an iterative method. Now we want to draw Cobweb diagram of this difference equation xn plus 1 equal to rxn, where r is a parameter not equal to 1. Step 1, this is the first order linear difference equation, r not equal to 1, the parameter. Note that when r greater than 0, and this difference equation is the Malthusian or exponential model for the discrete case. Step 2, draw a horizontal axis as xn axis and a vertical axis as xn plus 1 axis in the xn plus 1 plane. So this is the xn axis, this is horizontal axis, this is the vertical axis xn plus 1 axis, and in the xn plus 1 plane. Next, step 2. Step 3, draw the reproduction curve this xn plus 1 equal to rxn and the diagonal line xn plus 1 equal to xn. So we draw first the reproduction curve. This is the reproduction curve xn plus 1 equal to rxn when r is greater than 1, and this is the dotted straight line, dashed straight line, and this is the xn plus 1 equal to xn. Actually you can set this xn plus 1 as y and this xn as x. So this line is y equal to x passing through the origin, and this is equal to y equal to say 1.5x. So y equal to 1.5x, so r is greater than 1, so you can easily draw this reproduction curve. Next, step 4. Plot the initial value x0 on the xn axis and then move vertically upward to the reproduction curve 2 and mark the point x0 x1 on the curve 2 such that x1 equal to r x0. So this is choose this initial value, initial solution arbitrarily, this x0. So first we draw this vertical line up to the reproduction curve this, and then draw the horizontal line up to the diagonal line this. So this point is the x1, first approximation of this solution. Next we draw the vertical line up to the reproduction curve and then draw the horizontal line to the diagonal line, and corresponding this point on the x-axis is the x2. Next solution. next approximation of the solution. Next we draw the vertical line up to the reproduction curve, and next we draw the horizontal line up to the diagonal line. Now corresponding this point is x3. So this the solution sets this x0, x1, x2, x3. Now this solution set just move away from this steady state 0. The steady state is the point where the reproduction curve and this diagonal line meets at this point. The corresponding x coordinate is the steady state or fixed point or equilibrium point. So this solution set x0, x1, x2 move away this from the point steady state. So this is the x star equal to 0 is unstable steady state, and this is the Cobweb diagram for geometric growth. Here solutions diverge to up to infinity and so on. So geometric growth, this is the Cobweb for geometric growth. Now we draw by GeoAlgebra plotter. Is very interesting. First we set this xn plus 1 equal to rxn. So this is rxn equal to r equal to 1.5 greater than 1, this x. So rxn is this point. So xn plus 1 equal to rxn, xn equal to put here x, and xn plus 1 is y. So this is the y-axis, this is the x-axis. Choose x0, initial value is 2. Next now iterate this. So this corresponding this x1 point is 3, and this is the point 3, this x1 point 3. So we draw this next iterate this. So this point is this up to horizontal line, and corresponding is 3 point x1 solution is x1 is 3, and corresponding this is the x1 is 3, and next vertically upward this is the x1, and next iterate this x corresponding x3 equal to 6.75, corresponding point is 6.75. Sorry, this is the 6.75 is x3, and this x2 is the corresponding 4.5, and corresponding this point and the x-axis this 4.5, corresponding x2, and corresponding up to draw this horizontal line up to the this red color line is this xn plus 1 equal to xn, and this is the this violet color line is the r xn. Here r equal to 1.5 you choose here. So we observe that this x0 corresponding x1, this point corresponding x2, corresponding x3 move away from this intersecting point. This is the steady state of this. And when r is lies between 0 and 1, 0 less than r less than 1, and then we choose here x0 is here. So corresponding this dotted line and dashed line is the xn plus 1 equal to xn, and this is the diagonal line, and this is the reproduction curve when r 0 less than r less than 1. Say choose r equal to 0.5, and this is the y equal to 0.5x, this line reproduction curve. Choose here x0, draw this vertically upward to this point, and then horizontal up to the diagonal line. Next this draw to the reproduction curve and so on, this x1. So x0, x1, x2, and in this way moves closer to the point steady state here this. So this is the stable x star equal to 0 is stable steady state, and the Cobweb for geometric decay because r is 0 less than r less than 1. So this is the solution. Here the solutions converge to this x star equal to 0. Next, when r is less than minus 1, so put here y equal to say minus 1.5x. So this is the reproduction curve is here, and this is the dashed line is the xn plus 1 equal to xn, that is y equal to x, this line, and choose here x0. So x0 this and this to this and this. So this x1, and these two, and so these, so x0 x1 and move away from this point, steady state or fixed point from this. So this is the x star equal to 0 is unstable and solution diverge. And for when -1 less than or less than 0, put here say minus 0.5 are equal to minus 0.5. So we draw this is the reproduction curve is here, and this is the diagonal line. This choose x0 here, so x0 to here, reproduction curve, and diagonal line this and this to up to this, and this is the x1, this on this xn axis, this x1, so x0 this x1. So solution closer to this fixed point x star equal to 0. So x star equal to 0 is stable for -1 less than or less than 0. Next question. So this procedure is continued between the reproduction curve 2 and the diagonal line xn plus n equal to xn to obtain a set of solutions point x0, x1, x2 and plotted on the xn axis. Now for a fixed point x star, we have xn plus 1 equal to xn equal to x star, and put here value of x star on the give equation 2, xn plus 1 equal to rxn, so x star equal to rx star, and solving we get r not equal to 1, so x star equal to 0, and this is the only fixed point this, and this is the intersecting point between the diagonal line and the reproduction curve xn plus 1 equal to rxn. Next question, part B, this asymptotically stable this xn plus 1 equal to fxn and corresponding this one-dimensional discrete equation stability analysis of this. Let x star be a fixed point or steady state or equilibrium point or critical point of the one-dimensional system xn plus 1 equal to fxn, then x star is said to be locally asymptotically stable if a modulus of f dash x star is less than 1 and unstable if modulus of f dash x star is greater than 1. Second part, this is the difference equation, one-dimensional difference equation, and this for fixed point x star, we have xn plus 1 equal to xn equal to x star. So write here x star and xn by replaced by x star. So we get x star common, so 1 minus lambda k by k into k plus lambda minus 1 to x star. So either x star equal to 0 or from this factor this k plus bracket lambda minus 1 x star equal to lambda k. Solving this x star equal to k provided lambda not equal to 1. So we get two fixed points x star equal to 0 and x star equal to k, and if lambda not equal to 1. Now we are going to discuss that the stability analysis. Let xn plus 1 equal to fxn. So fx equal to lambda kx divided by k plus lambda minus 1 to x. We here replace xn by x. So this is the function of fx. So find with derivative with respect to x, f dash x, this lambda k constant divided by u by v method, and solving this f dash, simplifying this f dash x equal to lambda k square whole divided by bracket k plus lambda minus 1 to x whole square. For this point, critical point x star equal to 0, put here x star equal to 0 here, so f dash 0 equal to this lambda. So x star equal to 0, steady state x star equal to 0 is locally asymptotically stable if modulus of lambda is less than 1 and unstable if modulus of lambda greater than 1. Next, for the fixed point x star equal to k. Now f dash k equal to lambda k square whole divided by k plus bracket lambda minus 1 into k whole square, this is equal to 1 by lambda. So modulus of f dash k equal to modulus 1 by modulus of lambda. So the steady state x star equal to k is locally asymptotically stable if this modulus of f dash k is less than 1, that is 1 by modulus of lambda is less than 1, and that is if modulus of lambda is greater than 1, and unstable if 1 by modulus of lambda greater than 1, that is if modulus of lambda less than 1. Next question. Nine A. Let x star y star be a steady state of the two-dimensional discrete time system xn plus 1 equal to f xn yn plus 1 equal to g xn yn. Linearize the system about the point x star y star and hence state the conditions for stability of x star y star. Is the proof of this question part A. Consider system of first order nonlinear difference equations. This x, actually put here xn plus 1, replace here t by n. So xn plus 1 equal to f of xn comma yn, yn plus 1 equal to g xn comma yn. Here f and g are nonlinear functions with continuous second order partial derivatives. Steady states of the system. Let x star y star be a steady state or equilibrium point or fixed point or critical point of the given system, then x star equal to f of x star comma y star and y star equal to g of x star comma y star. Here we put x n plus 1 equal to xn equal to x star and yn plus 1 equal to yn equal to y star. Now linearization of the system 1 about the point critical point x star y star. Consider a small perturbation about the point x star y star by this un equal to xn minus x star, vn replace t by n equal to yn equal to y star. That is xn equal to un plus x star, yn equal to vn plus y star. Then the given system becomes this ut n plus 1 plus x star equal to f of un plus x star comma vn plus y star, vn plus 1 plus y star equal to g of un plus x star comma vn plus y star. Now if un plus x star comma vn plus y star by applying by Taylor's expansion about the fixed point x star y star and neglecting the second and higher degree terms due to small perturbation un vn. So this f of x star y star plus un del x of f of x star y star plus vn del y of f of x star y star. Now this equal to this f of x star y star equal to x star because x star equal to f of x star y star by 2, x star equal to f of x star y star because x star is the steady state, x star y star steady state. Next un into del x of f of x star y star plus vn del y of f of x star y star. Hence this ut plus 1 because it is f of un plus x star plus vn plus y star equal to this un plus 1 plus x star. So this equal to un plus 1 plus x star and this x star and this x star, this x star and this x star cancel. So ultimately we get un plus 1 equal to un del x f of x star y star plus vn del y of f of x star y star. Similarly, we can get vn plus 1 equal to un del x of g x star y star plus vn del x g x star y star. This system is called system 4, system 4. This is the linear approximation or linearization of the given nonlinear system 1 about the steady state x star y star. So this is the linear system, corresponding linear system corresponding to the given nonlinear system. Writing this in matrix form So we use here capital U n plus 1. Replace T by n. Capital U n plus 1 equal to capital J capital Un, where the Jacobian matrix or variational matrix J at the point x star y star is given by this 2 by 2 matrix del f del x, del del y of f, del del g of del del x of g, del del y of g, and this Un equal to small un small vn. This is the column matrix at this point x star y star, this Jacobian matrix. Call it this a11, a12, a21, a22, say. So del del x of f at the point x star y star equal to a11, del del y of f at the point x star y star equal to a12, del del x of g at the point x star y star equal to a21, del del y of g x star y star equal to a22. The eigenvalues of J determines the local stability of the system 1 at the critical point x star y star. Stability conditions. The characteristic equation is given by J minus lambda I. This is the J minus determinant of this J minus lambda I corresponding characteristic equation, and J is the corresponding evaluated at this point x star y star. So determinant of this matrix, this a11 minus lambda, a12, a21, a22 minus lambda equal to 0. So lambda square minus bracket a11 plus a22 into lambda plus a11 a22 minus a12 into a21 equal to 0. And this is the trace of the matrix this matrix J corresponding sum of the diagonal elements a1 principal diagonal elements a11 plus a22, and this is the value of the determinant J. So this characteristic equation reduces to lambda square minus trace J lambda plus determinant J equal to 0. Equation 5. The equilibrium point x star y star is locally asymptotically stable if and only if modulus of lambda j less than 1. That means if lambda 1 less than 1 and lambda 2 modulus of lambda 2 less than 1. The condition is that modulus of trace j is less than 1 plus determinant of j less than 2. We can prove it, but in this question linearize the system x star y star and hence state the conditions. No proof here asked here, and very difficult to prove this condition and lengthy cumbersome proof here. So he only here state the condition of the stability x star y star. So condition of stability is this condition of stability is this modulus of stress j is less than 1 plus determinant of j less than 2. This is the condition for the locally asymptotically stable of the equilibrium point or steady state x star y star. Next question part B. Show that coexistence equilibrium point of the Nicholson-Bailey model h n plus 1 equal to bhn e to the power minus apn, pn plus 1 equal to chn bracket 1 minus e to the power minus apn is always unstable. Now Nicholson-Bailey model is the classic two-dimensional discrete time model of population biology and is represented by this. In t plus 1 or the question here h and p, here we use n and p, so this h b, here this r is b and n is h and p is, so write this, replace this n by h. and P by P, no replacement here, so P is B, and B and C, so this R is B, replaced by R is B, and C, and A. So this AA. So if possible, replace this N by capital H and this R by small b, and no replacement for P. So delete this. So only replacement is this N by capital H and R by small b, where in T, here in small n, T by small n, and T small t by small n, small t by small n. So here put small n, H small n plus 1, P small n plus 1, B this capital H small n e to the power minus a p n, where this nt is the density of the host population in the tth generation, and pt is the replaced accordingly, t by n and n by a capital H and r by b, this density of the parasitoid population in the tth generation, and so on. Now for equilibrium points of the system 1 are given by nt plus 1 equal to nt equal to n, and pt plus 1 equal to pt equal to p, say then from the system, given system, we can write n equal to r n e to the power minus ap is equal to this function f of np, say, and this p equal to c n bracket 1 minus e to the power minus ap is equal to g function g of n comma p, say. This system 2. It gives a trivial equilibrium E naught, this is equal to 0, 0. This taking common n from the first equation, so n equal to 0, and this put n equal to 0, and if from the second equation we this n equal to 0 and p equal to 0, and the non-trivial solution equilibrium point, this star, this for n star and p star, where n star and p star is determined by this 1 equal to because n is common, taking common n common, this 1 equal to r e to the power minus a p star, and p star equal to c n star bracket 1 minus e to the power a p star. And this p equal to 0 because this 1 equal to r, this r non-zero quantity, so this e to the power p equal to 0 from this, and p star equal to this from first equation, e to the power minus a p star equal to 1 by r, so e to the power a p star equal to r, this implies p star equal to 1 by a log to the base e, that is ln r. Substituting this in the second equation, we get put this value of p star in the second equation, so 1 by a ln r equal to c n star bracket 1 minus this minus 1 by r, because this is equal to 1 by r. So n star equal to r ln r whole divided by a c bracket r minus 1. Thus the interior equilibrium point is given by E star equal to n star p star, where n star equal to this r ln r by ac bracket r minus 1 and p star equal to this 1 by a ln r. This equilibrium is feasible, that means biologically meaningful, if n star is greater than 0 and p star is greater than 0, greater than equal to 0, both are non-negative. So if r minus 1 is greater than 1, r minus 1 greater than 0, so r is greater than 1 if r is greater than 1, otherwise both n star and p star will be negative. At an arbitrary equilibrium point in P, the Jacobian matrix is given by this matrix 2 by 2 matrix del del n of f del del p of f del del n of g del del p of g. So partial derivative with respect to n and p, we get actually f equal to this function, this r n e to the power minus ap, and g equal to c n bracket 1 minus e to the power minus ap. So differentiating partially, we get r e to the power minus ap minus ar n e to the power minus ap for this del del p of f, and del del n of g equal to c bracket 1 minus e to the power minus ap, and del p of g equal to ac n e to the power minus ap. At the trivial equilibrium E naught 0, 0, the Jacobian is given by this matrix R0 C0. So the eigenvalues are lambda 1 equal to R, lambda 2 equal to 0. Thus modulus of lambda 1 and modulus of lambda 2 will be less than 1 if R is less than 1, because R is positive, and the trivial equilibrium will be stable, implying that both species will go to extinction, that is abolish, both species are going to abolish. Note that whenever E naught is stable, then the interior equilibrium, that is also called coexistence equilibrium, n star p star does not exist, because if R is less than 1, then this existence for this we must have r greater than 1 for existence of this star. So in this case, when star is stable, then the interior equilibrium or coexistence equilibrium star, the n star comma p star, does not exist. Now at this point, steady star, the Jacobian value is this, Jacobian is this j n star p star. So we write here, just write p star, n star and p star here. So p star n by n star, p by p star, and so on. Now using the result e to the power minus a p star equal to 1 by r. So put here we get 1 minus a n star c bracket 1 minus 1 by r a c n star 1 by r by the first equation of 3. First equation of 3, this. Hence trace of j, this is the sum of the principal diagonal elements, this 1 plus ac n star 1 by r and determinant of j is this into this minus this into this. So this ac n star by r plus ac n star bracket 1 minus 1 by r. So we get this ac n star, and equation 4, this n star equal to this. So put here n star equal to this, so r by r minus 1 into ln r, that is log to the base er. We show that determinant j is always greater than 1, hence star is always unstable, because by Raoult-Hardy rule, this determinant j must be less than 1. Now determinant j greater than 1 implies r by r minus 1 ln r greater than 1, and implies r ln r is greater than r minus 1. This implies minus r ln r less than 1 minus r. This implies r minus 1 minus r ln r less than 0. Let this h r equal to r minus 1 minus r ln r. So h1 equal to 0, and h dash r equal to minus ln r less than 0. Therefore, hr is a decreasing function of r for all r greater than equal to 1. Since h1 equal to 0, so for r equal to 1, so this is the function, this corresponding h1 equal to 0 for r equal to this. So next, hr will negative for all r greater than 1. So from this point, hr negative this, because this is the hr function, and this is the this axis r axis, and this vertical axis is hr. So this point is 1, this 0, and this point is 1. So at this point h1 this is equal to 0 for r equal to 1, but decreasing function of r for all r greater than equal to 1. So decreasing function means this decreasing function hr. So obviously hr will be negative for all r greater than 1. Hence this hr is decreasing negative. So hr is negative function. So r minus 1 minus r ln r less than 0 for all r greater than 1. This is implying that determinant j always greater than 1. So coexistence equilibrium E star can never be stable. Hence the proof. Thank you for watching this video.